Hi guys, I am Bandro. Currently I'm pursuing my PhD at National Institute for Space Research. And I'm not going to present any work I developed. I'm going to expose some thoughts I have when I was working. I work in the industry, and also I'm studying. I'm a doctor pursuing my PhD, right? So I would like to make a question. Have you ever been frustrated by not being able to reproduce or scale academic work? I don't know how many of them all of you are from remote sensing field, but that's a very common problem. We got some paper who was published, and they report very good results. But when we try to reproduce them or to make them work in a productive field, productive scenario, it doesn't work. And it's obvious it doesn't work because they don't provide the source code, they don't provide training data, and when the source code and training data are available, it's hard to reproduce the very same results for a series of reasons. But although people are not providing source code or training data, there's another problem that difficult the reproducibility of these works, which are people tend to use data, samples data that are spatially correlated. In other words, when we are talking about machine learning, AI, data points which are close, which are kept together, they are spatially correlated, and we cannot generalize. For example, here in this figure at the right, you can see these little points in red as a points, for example, published in the study in the Amazon here in Pará. But if you try to extrapolate this work and take the model made with these little red points and try to predict the very same model to the green points, you will incur in bad results, bad accuracy, low values of accuracy. That's why, because the model is overfitted. It's overfitted to this region. And she doesn't learn the patterns from the other regions. That's basic, but that's the reality for most of the papers we see in the scientific literature. And that's what happened. You get, this is a Brazilian meme. You expect something because you see they reported good results, but that's what you've got. You become sad because it doesn't work as you expected. And actually, there's a long way, a long path you have to follow to transform that academic work into a industry product. Okay. So, despite limitations, remote sensing academic works that resort to deep learning achieved good accuracy improvements. In the last decade and now, they used a lot of simple, shallow architectures, relatively shallow architectures, like convolutional neural networks, represented, for example, by UNet, which is broadly used by the remote sensing community. You have the temporal CNNs, which are convolutional neural networks that can account with time. They can see multi-temporal remote sensing images. And even recurrent neural networks, which are a special case that can analyze sequential data, which I used in my master dissertation. They outperformed shallow machine learning for some mapping tasks. So at some extent, They really work. They got better results than they got before, but they have some serious limitations. Here you can see this graph. This graph represents how deep learning thrives over a big amount of data. Deep learning basically doesn't saturate. Here you can see traditional learning curve, which the performance of the model rapidly reaches a plateau with the increasing amount of data. Small neural networks, it's a kind of better, medium, it's better, even more better, and large neural networks tend to achieve this plateau a lot with very amount of data. So what does it mean? As the research evolves, models from deep learning are growing large. They have a lot of billions of parameters, thousands of billions of parameters, and we came to this kind of architecture called transformers. Since 2017, they got very popular. They were stimulated by a paper called "Attention is All You Need." These models, they have some attention mechanisms that avoid the need to recurrent loops into those architectures. So this make be able to parallelize the process in GPUs in a very efficient way, better than the recurrent neural network. So they basically replaced the recurrent neural networks. But these models are gigantic. The data set used to train, they are also gigantic, over 1 million samples. They show the need for high performance computing. You cannot train those models with few GPUs and few computers. You need clusters and plenty of GPUs. And they leverage transfer learning, which are something very important here to this talk. I will say about them in a few minutes. The computational intensive scenario limits the development of academic studies. Brazil, at least, most of universities don't have many resources to go to this kind of research, which is computational intensive. So this led big techs to have the monopoly of the state-of-the-art models. GPT, which is the backend of ChatGPT, owned by OpenAI, sorry. Gemini from Google, DALL-E from OpenAI, Midjourney. These two last are vision generative models. The two first are large language models. No, Gemini is actually a multimodal model, yeah. However, their focus isn't remote sensing data. They were trained to understand regular images, RGB images, cats, dogs, plants, and not multispectral or multitemporal data sets. And another problem, the annotation of the remote sensed imagery tends to be much more expensive than this other kind of data that these models deal with. And on top of that, remote sensing data sets are much more complex than the data sets usually used by these guys. Basically, GPT and Gemini, they work with something called corpus, which is trillions of tokens of text and make embeddings out of it. And that's why they are good. But they are good because they work with trillions of tokens. The same apply to DALL-E and Midjourney, hundreds of millions of images in order to converge. So but there's a light at the end of the tunnel. Transfer learning. Isn't nothing new, transfer learning, but I think that it's a movement that the remote sensing community have to do as quick as possible in order to keep the pace with other fields of research. What the transfer learner enables us? The use of pre-trained models. It also dramatically reduces deep learning hungry for training samples, which is a general problem, and potentially reduces the training time of the models. Here, at the bottom, you can see, I don't know how much you are familiar with neural networks, but I will roughly explain quickly here how does it works. It's a bunch of units connected one each other. They are called neurons because they resemble our nerve system. And at the left, we have the first input layer, which receives the data. The data gets transformed through all these units over the network. And here, at the other side of the network, you have the output, the result you want to the task you are trying to solve. And that's it. The training of these guys involves a part called feed forward, which is feeding that network from left to right to transform the data towards the right. And when you get some output of this, you can calculate the error, and based on the error, there's an algorithm called backpropagation. And this algorithm is able to propagate back the error signal and adjust the weights of these neurons. These adjustments take place a lot of times until the network gets the result expected. So it's basically that. What's the difference of transfer learning for what has been before? Transfer learning basically takes some network which was already being trained and take advantage of that, leverage that network to solve another task, which wasn't the original task used to train the original network. So here in red, you have neurons from a pre-trained model, a model we take and don't mess with that, and the blue ones, the appended neurons, neurons that we append to that network in order to train only those blue neurons to train the task we want to solve, to our problem. This is very necessary to reduce the amount of training samples we need to converge the network. And works pretty well. This part, this red part, is often called backbone, which is a part that is shared among the community in order for people to produce other models from that on. There are plenty of pre-trained backbones freely available. I will give two examples only, the ResNet 50 and ResNet 101. The first have 25.6 million parameters, the other have 44.5 million parameters. And they were trained with this amount of images. Those models, they resolve a simple task. It's just given that image, which is what class does image pertain. So you still have one cat. You say this image have one cat. You have a dog, have a dog. A house. You say that image has a house. So that it's simple as that. Those models. They were trained with this data set, ImageNet. This data set was created by a bunch of specialists in computer vision. And, but they have these characteristics. They are RGB images. They aren't multispectral images like remote sensing. So let's talk a bit more about this ImageNet. ImageNet, beyond being a data set, which can be used to benchmark models, it have also competition, a challenge that call people to, based on this data set, people make models in order to improve accuracy from the task of image classification. So you can see that before 2010, 2011, the error rate were 28%, 26%, and from 2012 on, they decreased a lot, 10% decrease of their error rate. That's why, because we started to use deep learning. That was the point where deep learning was considered a revolution in the field. So since then, the error was ramping down. And the human accuracy is 5%. So 2015 on, the error rate is better than the human efficiency. The computer now do this task better than the humans. And all this evolution was possible because this challenge and because of this data set, which is open. In the last decade and on, there was a profusion of computer vision challenges driving the development of the field. By winning these contests, many models proved themselves to be very useful in various other kind of tasks, not only image classification, also text, image segmentation, translation, speech to text, and so on. Naturally, through transfer learning, many new models was built upon previous ones. So that's a phenomenon important to note. People don't try to train out of nothing from scratch. At some point, the models become so big they have to, from that point on, continue their research. It turns out that most of these pre-trained models aren't that useful when used with multispectral and multi-temporal remote sensing imagery, since there's a big divergence in the input data shape and the distribution of this data. So they aren't fitted, they aren't tailored to remote sensing data. Although it's possible to use them. I have already used them in my works, and it works more or less, but it could be better. There are a number of available remote sensing databases associated to machine learning contests, but most of them are restricted to RGB channels and or to local scale areas of interest. So we have a little bunches of data. They are not integrated together. It's hard to have one single point in which you can use to gather them and compare them. There's these guys, Hugging Face and Kaggle. These machine learning sharing platforms, sharing/contest platforms, they are not tailored to remote sensing data. They are hugely used by other fields, but few used to remote sensing data. By the way, Hugging Face hosted a 1-year-long research workshop called Big Science, which built the first fully open source large model, the Bloom, which is, you can compare him with GPT and other models. It's completely open and was hosted by this kind of platform. The development of Bloom have the help of more than 1,000 researchers, and become an important landmark for open science. So it's a good example for us to see the importance of this kind of institutions, and how can we take these examples in remote sensing. So a wide open remote sensing oriented machine learning platform can be a solution that addresses annotations scarcity. As I said before, for annotation of remote sensing data, we need specialists, people who can interpret landscapes, people who can transform the data, make spectral indices in order to extract information of this data. So it's very expensive to annotate those data. A lack of remote sensing pre-trained backbones, it will be also addressed by this kind of proposal. Need to account for imagery metadata for stratification and training samples characterization. For example, what kind of metadata? Quality assessment bands, geometry acquisition, atmospheric correction. You have to know which kind of process has been done there. The processing level of the product. Here, of course, I'm talking about raster. Cloud covering, and so on. This can be used to optimize the design of the samples, used to train those models. Those kind of information they are barely used today in order to train deep learning models in remote sensing. They could be used not only for stratification and design of training samples, but they can be used as multi-model models along with the raster itself. It could be a big improvement. Need to account to temporal information. There's a need to account to temporal information, what is addressed with multi-temporal, taking into account multi-temporal aspect, using data cubes and so on. Data provenience, we have to know where each piece of data came from and the metadata associated to it. Isn't that so straightforward? And we need that in order to optimize training. And transferability. It's something that those platforms can help. I will show one example of it, of the transferability, which was, I showed to you in the first slide, these points, which were used to train a model to classify, to make a map here inside this little box, this area of interest in Pará. If someone wants to do the same task here in that other area, he can gather his points there and start to train a new model from scratch. But with transfer learning, this guy can take the other model who was already trained in another place and his new data points and start the training over the previous model. This is way, way better than train a new model from scratch here. So it's if we have a platform which people can share those kind of data, we can not only put data set together, make a union of these points, but we can share models that will grow stronger every day and evolve continuously. The same way, here's just an example I'm giving of this kind of stuff that can be done with that. It's another way around. This is induction. You take some points. The problem of take some points inside these boxes and try to predict outside, it's called induction. You have a particular case and try to generalize it. It's a problem. You have the opposite problem. You have the general, which is deduction reasoning, which we take points from all the area we can maybe someday map and try to map these particular areas. When this is made, these particular areas are also not very well represented, and you incur in bad assessment metrics. So What can I say about this guys? You can make the other way around. You can train a model with the green points. And with this model, you can later specialize your model you want to use in the specific region with this pre-trained model. So if you do that, you will have way better results than if you would train only with the red points, the same applied to the blue points. So that's why the deep learning evolved last years, and those platforms thrived. That's because the power of sharing and the openness of the data and the models. If that wasn't true, it wasn't happen. And there's no free lunch. In order to have those kind of systems where users can upload data, share data, process, generate models, and share the models generated, you need GPU workloads, you need storage, parallel and distributed processing, cloud credits, etc. It's obvious. And where is the interaction between the industry and the academy there? The government, when I say industry, it's in the general way. Government, private companies, NGOs should foster open source platforms, remote sensing open source platforms, because individually, those entities cannot evolve the field at proper pace. It simply is unfeasible. We have to sum efforts in order to have the data in the amount we need. Not even big tech companies could achieve that alone. So we have to sum efforts. Joint effort has to take place to establish standards, common training, and common tools. Otherwise, there will be a lot of wasted money, which is what happens when we have silos of data and models and they don't connect together. So it's simple as that. It's just that thinking I would like to share with you guys. Thank you.